All right, this is going to look at the second formative in the free fall unit, and we're going to look at LT5b in this video. I'm going to go over these equations briefly, just in case you didn't watch the first video. But if you just watched the first video and you don't want to go over the equations again, because I went over them there, feel free to skip ahead. All right, so the equations, there's several groups of them. These are the motion equations for predicting motion. These are the energy equations for dealing with energy. And then here we have the forces equation. And this is a little fact down here from free fall about the acceleration of objects. For proportional reasoning, when you're doing stuff with the motion equations, you want to use these lower set here. And one of the things with proportional reasoning is you can't really do it, or there's some special things you need to do that we're not showing you or requiring you to do in this class. You can't do proportional reasoning if you have pluses and minuses in those equations. So you'll see here, see how that doesn't have a plus or a minus in it? And this one does. Now delta x, delta just means final minus initial. That's what delta means. So this one here, there's no plus or minus in it. And this one here, there is a plus or minus in it. But what's going to happen is this is the initial velocity. You're going to choose the initial point to be a spot where that initial velocity is 0. And then you can write, oh, this becomes 0. And that will make it so there will be no plus or minuses when doing proportional reasoning. Okay? All right, number 2. Oh, number 1. There, okay, good. Number 1, so Ben and Cooper are having a competition to see who can jump higher. Both boys start with the same initial velocity. Make sure we get that. But Ben has mass, it's 1.5, greater than Cooper's mass. All right, I believe it. Cooper jumps 1.2 meters off the ground. Okay, maybe they're on trampolines or something. So let's set this up as energy problems. So when they're jumping off the ground, at the bottom, they are moving. At the bottom, they're moving, and at the top, their velocity is 0. So they're going to have kinetic energy to start with and just gravitational energy to end with, and we're not transferring any energy in or out. So let's do a conservation of energy tech. We start with 3 boxes of energy. We add 0 energy. We better end up with 3, and in fact, we do. So kinetic energy is 1/2 mv squared. Energy stored gravitationally is mgh. And we're going to show our work down here. Remember, you want to show and write out your equation. You can do it in several different ways. We do need to see the equation just variable form. So if you just start with this thing here, that will not be sufficient. So notice that this equation here is just copied down to here. So 1/2 mv squared. And then what we did here is we put in the factors of change. So 1/2 if we're comparing Ben to Cooper, does the 1/2 in the equation change? No. So its factor of change is just a 1. The mass, Ben's mass is 1.5 times more. And Ben's velocity, the same initial velocity, so that's a 1 out in front there. And now, so this is how the left-hand side of his equation is changing. How's the right-hand side? Well, his mass is 1.5 times bigger. The gravitational field strength is the same. They're both on Earth. Ben might be an alien, though, or at least a monster. And the height, we want to know, how does the height change? So what we're going to do is we're going to write a new equation with just these factors of change. Or you may have written it just with the variables, and then you're going to go to this equation here. Either one is okay. So I'm just going to write the factors of change here. So 1 times 1.5 times 1 equals 1.5 times 1 times question mark. Now this equal sign here means these sides have to be exactly the same. So I have to figure out what needs to go on my right-hand side, that x, so those equations are equal. Well, 1 times 1.5 times 1.5 equals 1.5 times question mark. Well, question mark is just 1. Now, I'm like, I did all that work for nothing. Does that make sense, though? If they have the same initial velocity, if their masses are different, should they jump the same exact height? So let's write our answer here. Height is the same in this case, in the same. Otherwise, we'd write like 1.5 times more or 0.5 times as much. So because Ben has more mass, he has more kinetic energy. But also because he has more mass, he can have more UG, and those two things balance out. So what is Ben's jump height? Well, 1 times 1.2 here. Cooper's jump height is 1.2. We get the same thing. So that was one where there was no change. All right, Mr. Melky is working on increasing his jump height. The first time he jumps, it takes him 0.2 seconds to reach his maximum height. After training, he has increased his jump height to be 9 times higher. By what factor is the time different? So for part A, we're not looking at specific numbers, so ignore this for right now. We're looking at the 9 times higher. So we're going to use a delta X equation. We're going to use a motion equation here because our energy equations don't have time in them. And these equations don't have time in them. So we're looking at by what factor is the time different. And we know about the height, so we're going to use this one right here because this is a acceleration equation because we can't use this because we're accelerating here, and it has a height in it. So we're going to start off with this equation here. We're going to show that the velocity is 0 at the top. So really what we're doing is he goes up and then comes back down, and we're starting here and we're saying, whoop. We're saying that is going to take. Well, originally it took 0.2 seconds. We don't need to worry about that right now. But this distance here is now 9 times more. So how do we do that? Well, I'm starting here. I'm going to do a fall problem. It doesn't matter if we do a jump up or a fall because of symmetry. So I'm going to say, hey, his velocity is 0 here at the top, right there. And, well, he's 9 times higher. The 1/2 doesn't change at all. It's still 1/2. The acceleration doesn't change at all. He's still in free fall. And then we want to know the time. Now, watch out here. That's time squared. So we've got to be super, super careful. So on the left-hand side of this equal sign, we have a 9. On the right-hand side, we have 1 times something squared. So we got to ask ourselves, what squared gives us 9? So you can solve that by taking the square root. And so the answer is 3. 3 squared equals 9. So we could write out our answer here. Time is 3 times more. And then we have to actually find out what's his new time in the air. Well, if his first one was 0.2 seconds, 3 times more is going to be 3 times 0.2, so 0.6 seconds. Number 3. So let's see. Mr. Wolf is jumping down from the counters of his classroom with drawing on the whiteboards. The first counter has a height of 0.5 meters. Takes Mr. Wolf twice as much time to jump down from the second counter. So the time is changing. We want to know how does the height different. All right, so he's starting here and he's jumping down, okay? And then the second counter, it took him more time, 2 times the time. And so we want to know how is the height different. Again, we're going to use the same equation for all the same reasons we used earlier. We're dealing with height here. And we want to look at like, okay, how far is he falling here? You can use the delta x one and then just look at delta x. Or here, as another example, we used one without delta x. And we said, oh, the final position is 0. He's on the ground at the end, so this one goes away. And then we just moved this over algebraically by subtracting x naught from both sides. His initial velocity, because he's jumping down from the counter here, is 0. And so this is the equation we are working with. So let's see. How does the x not change? So at this point here, we're just looking at factors of change. So since this is just a negative sign, it's not subtracting anything, we can really just ignore it. Or we can look at, okay, how does the negative 1 change? It doesn't. Like as he goes from here to here, this equation, that's a constant in this equation. It's a factor of change of 1. How does his initial position change? We don't know. The 1/2 doesn't change, so we get a 1. Acceleration doesn't change, so we get a 1. And we're told that the time doubled. Now, the time doubled, it's squared. So that's got to be 2 squared. So the left-hand side, we have 1 times question mark times 1, so just question mark. The right-hand side, we have 1 times 2 or 1 times 2 squared. So the question mark equals 2 squared, so it's 4. So the x naught is now 4 times more, right? So he must be jumping off of a counter that is 4 times higher. So if the first one's half a meter, the new counter, oh my goodness, is 2 meters tall. All right, last one. Mrs. Rona dropping candy off her balcony to trick-or-treaters below. The first time she drops a fun-size Snickers bar, and the second time she drops a king-size, so much larger Snickers bar that has 3 times the mass. All right, so what other variables besides mass is changing? Let's read this whole thing before we answer these. By what factor is a variable identified different when the candy has 3 times the mass? Ooh, the net force on the candy, calculate the new variable. Okay, so we're looking at F net equals MA or FG equals MG. So if there's more mass, if we were to draw an FBD, so here's the first one, and then here's the second one, the bigger force of gravity. So the net force is changing. And I'll show you how to do this. If you said FG, I'll show you how you could do that as well. By what factor is a variable you identified in A different from when the candy has 3 times the mass? Well, 3 times the mass, the same acceleration. You have to realize it's the same exact acceleration because they're both in free fall. So the mass has to be, or the net force has to be 3 times as much. The original net force on the candy was 3.4 newtons. So we're going to do 3 times 3.4 is 10.2 newtons. You could also say FG is changing, and you could do this equation here. This would be fine. And you'd say, well, 3 times the mass, the gravitational field strength is the same. So question mark equals 3. So FG is 3 times more. You knew that the net force was 3.4. The force of gravity is 3.4. So you get the same answer in the end. Either one of those is fine if you thought about that in a different